Now let's go ahead and explain that last problem using equipotential lines, which are like contour lines. Here is a graph for electric potential near a positive charge Q, which resides in the XY plane. And in fact, right here, this line right there is 0, R equals 0 right there. This green area is an area in which it's a range of potential values. These circles that go around right here, this is an equipotential line. Here's another equipotential line, that circle. Here's another equipotential line. And these are just, in the green is a range of values. That's a range of values. That's a range of values. So they act just like contour lines, these equipotential lines. As you get closer to the charge, the potential goes up. KQ over R is lower, the potential is higher. So as you get closer to the charge, the electric potential goes up. A positive test charge that you bring near it from the right would want to move to the right. A positive charge would want to roll down this hill. Now the bold line outlining the right of the figure, that is simply a graph of KQ over R, where R is the distance from the charge. Now we're in the XY plane, so you could calculate R by square root of x squared plus y squared, square root of that quantity. But this, notice that that's just like the graph we just drew. It's 1 over R is what it's proportional to. In fact, it's KQ over R to be exact. Now, this outermost region, which is floating above the XY plane, it actually keeps getting lower and lower and lower. This is graphing electric potential, by the way. Where does this blue region actually meet the XY plane? In other words, where potential is 0. How far away from this point does it meet the XY plane? That's just asking, where is the potential 0? Well, infinitely far away from this charge, it eventually will get to 0. If you look at this sideways, it looks just like this graph that we have here. This is a really difficult graph to make yourself. But what's easy for us is to look at it from the top down. In other words, we're going to make a two-dimensional representation of this. And this is what that looks like. These circles are equipotential lines, okay? And I've drawn in the field lines here as well. Now note that the electric field lines in red, due to this point charge on the left, the point charge is right in the center. Notice that where the field is strongest is where the E field lines are right in there, where they're closest together. We also find, you see all these lines, now the regions are just ranges of values, but the lines are equipotential lines, this line there, this line there, this line out there. We also find that the equipotential lines are closest together. Thus, where the field is strongest, the potential gradient, i.e. the hill, is steepest. You could just, as long as this inside of the red line, the inside of the orange line, the inside of the yellow, and the inside of the green, as long as those are equally spaced equipotentials, for example, maybe it starts at 10 volts, 9 volts, 8 volts, 7 volts, 6 volts, as long as they're equally, the differences are equal magnitudes, they will get spaced farther apart, and right here is where those equipotential lines are closest. It's steepest, that means the field is strongest. Note that two-dimensional equipotential lines, in actuality, are in 3 dimensions. Those are equipotential surfaces. This is a circle. What would an equipotential surface look like? What shape would be the object that has all the same potential relative to infinity due to that point charge? Instead of a circle, we would have an equipotential sphere. It would be a sphere around that all has the same potential.